Welcome to Mechanical Drawing and Design N6. Today's presentation is going to be on chems. This is not a long module and it is not that difficult to understand. So if you pay attention to this presentation, you should be able by the end of the presentation to solve any problem you may get in your exam on this module. Let's begin. First, we will look at chems. What are chems? Okay. I'm gonna give you a small illustration of how they work so that you can begin to make sense of what chems are. And so basically what you're looking at your screen is a chem that is in action. Okay, so the chem is actually this member that we have at the bottom that is rotating about that axis. Okay, this is what we call the chem. And what I want you to see is that because of the angular velocity of the chem and also the shape of the chem, this member here is forced to react to that, okay? And because of that, then this member is also moving in a specific way. And so we refer to that member there as the follower. Okay, the follower is pretty much the member that is responding to the motion of the chem. And not only does it respond to the motion of the chem, but it also responds to its shape, okay? And another thing that is very important for me to point out here is the distance from the lowest point that the follower can reach to the highest point that it reaches. Okay, if you measure that distance, which can be thought of as the stroke length of the follower, okay, that distance is what we will refer to as the rise or the lift if the follower is going up, or we may also refer to it as the fall if the follower is coming down, and that is that distance there. Okay, so the lowest point that the roller on the follower can reach, okay, the distance from that point to the highest point that the roller on the follower can reach, which is there. So if you measure that distance, this is what we will refer to as the rise or lift if the follower is going up. And we will also refer to it as the fall, okay, if the follower is coming down. And as I said earlier, one way of thinking of it is the stroke length of the follower. You can see it as the stroke length of the follower. Okay, very important. Now, back to what I was explaining. I said that the motion of the follower is dependent on the angular velocity of the cam, but also the shape of the cam, okay? And now you will see that if you have a cam that has got a different shape, the follower will behave differently, even if you have the same angular velocity, which is the case that you see in this picture here. Now we have a cam that has got a different shape but the same angular velocity. But now if you look at the motion of the follower, you will see that the follower has a different motion. Okay, of course this is the cam, that's the follower, and of course here we have the rise or fall distance. Okay, so you can see that because we have a different shape of the cam, although we have the same angular velocity, this follower is not behaving the same way. When you look at the follower on top, you can see that it rises, it falls, and then it waits. It rises, it falls, and then it waits. By the way, when the follower is waiting, we refer to that as dwelling, okay? So we will say that the follower rises, falls, and dwells, okay? So this is what it does here. It rises, it falls, and then it dwells. But if you look at the follower on this side, you will see that what it does, it rises, it dwells, and then it falls, it dwells, okay? Look at it carefully, you will see, okay? It rises, dwells, falls, dwells, rises, dwells, falls, dwells. Okay, so you can see that you have a different behavior for the follower at the bottom than that at the top. Okay, and this is simply due to the fact that the chems have different shapes. And so what is really important to observe here is that in mechanical engineering, you may want to design something that does a certain motion in a specific manner. And so for you to be able to do that, one thing you can do is to use a chem system. Okay, and you will just give the chem a specific shape that will then cause the follower to behave in a certain way so that you can achieve whatever it is you want to achieve. Maybe you may want something to press some button. Maybe you can have a design where you want something to press a button once and hold and then let go, and then press again once and hold and then let go. Then you can connect that button to a cam system like this one, okay? Because then it will press, hold, let go, and then it will press, hold, let go, then it will press, hold, and let go. Okay, you see what I mean? And so depending on the type of mechanical application you have in front of you, you can design a cam system to allow you to actually achieve that. Okay, very, very important. But what I want you to see at this point is that the motion of the follower is essentially dependent on the shape of the cam and also the angular velocity of the cam, because if we spin the cam faster, the follower will also move faster. Okay, very, very important. Now, cams can be classified according to the motion of the cam. Okay, you can classify cams according to the motion of the cam. If you look at these cams here, that one and that one, you can see that they are both rotating. Okay, and this is the type of cams that you need to know for this particular module. Okay, we will tackle rotating cams. Okay, but you can also have cams that are reciprocating. To reciprocate means to move back and forth. Okay, so you can have cams that move back and forth, but for this module and for the purpose of mechanical drawing and design N6, you are only expected to know about cams that are rotating, the type that you see in these pictures. Okay, cams can also be classified according to shape, and there you have radial cams, cylindrical cams, wedges, spherical cams, conical cams, and inverse cams. Okay, according to their shapes, you can also qualify them. If you look at these cams, because they are rotating about a specific axis, these can be regarded as radial cams. Okay, because it's almost as if you have a center here and a certain radius, and then the cam is just rotating. Okay, so these can be regarded as radial cams. Okay, but you can also have cylindrical, wedges, spherical, conical, and inverse cams. Okay, so this is if we're qualifying them according to their shapes. Those are the main different cams you can get. But cams can also be qualified according to the motion of the follower. And this is really, really important, because this is what will lead us into even deriving the equations that we need to be able to solve problems on cams. Now, if we are classifying cams according to the motion of the follower, you will have cams that dwell, rise, dwell, and then fall. Okay, so this is what we refer to as a DRD, because the cam, the cam will cause the follower to dwell, and then to rise, and then to dwell, and then to fall. Okay, so although they didn't write fall here, it's because it is assumed that if the follower has risen previously, of course, the next thing that it will do is fall. Okay, so those followers that behave like that, those will be what we will refer to as dwell, rise, dwell. Okay, DRD cams. Okay, those are the ones that cause the follower to dwell, rise, and dwell. Okay, but you also have cams that will cause the follower to dwell, rise, fall, dwell. Okay, and these will be the DRFD cams. Okay, they cause the follower to dwell, rise, fall, and then dwell. And then you will have cams that cause the follower to rise, return. Return here is the same thing as fall. Okay, and then rise. So if you have cams that cause followers to rise, fall, without any dwelling in between, then those are referred to as RRR cams. Okay, triple R cams, because they cause the follower to rise, return, rise, return. Okay, so triple R cams are the ones that do that. So we can also classify cams according to the motions of the followers. So now let us look at these two cam systems that we have and try and determine which they are. Okay, what motion of the follower can we observe with these cams? Okay, so let us look carefully at the first one here. Okay, what will you say that the follower is doing? From what I see, the follower is dwelling, rising, falling, dwelling, rising, falling, dwelling. Okay, so it dwells, rises, falls, dwells, rises, falls, dwells. And so if you look carefully at this table, you will see that that is a DRFD cam. Okay, this is a DRFD cam because this cam is causing the follower to dwell, rise, fall, and then dwell again, and then it repeats. Okay, so this is a DRFD cam. Let us look at this one. What is the follower doing in this case? If you look at it carefully, you will see that it dwells, rises, dwells, and then falls. Dwells, rises, dwells, and then falls. Okay, if you look at it, look, it dwells, falls. Okay, I hope you can see what it's doing. Okay, dwells, rises, dwells, falls. Dwells, rises, dwells, falls. Okay, and so if you look at it, you will see that this is actually a DRD. Okay, it is a DRD cam because what it is doing is that it dwells, it rises, dwells, falls, dwells, rises, dwells, falls, dwells, rises, dwells. Okay, so it's dwell, rise, dwell, fall. Okay, so it's a DRD cam. Okay, so that's what we have here. I hope this made sense. If it didn't, you can just look at these cams again and try to see which type of follower motion you have, and you will see that it is exactly as I showed you. And so moving right along, we will now look at the followers themselves. Okay, we have different types of followers that we can have. You have the ones that are like this. If you look carefully here, you will see that the point of contact between the cam and the follower is pretty much just like a point, okay? And so when you have a follower that has got that type of contact with the cam, it's called a knife edge follower. Okay, this is a knife edge follower. The one that is like this, that's got a roller making contact with the cam, which is what we see here. Okay, this is pretty much a roller follower. But sometimes you can also have a follower that has got a flat surface like this, okay, a face like that, when at its point of contact with the cam, okay, and so that is what you will refer to as the plane face follower. Okay, this is the plane face follower. And then you can have one that is like this, okay, and that is what we will refer to as the spherical face follower. Basically, we classify these followers depending on the point of contact they have with the cam. Okay, what component do they have that makes contact with the cam? Okay, so that is what tells us how to label the followers. When you just have an edge, a pointed edge like this, then this is a knife edge follower. When you have a roller, okay, that is used for contact with the cam, then that is a roller follower. Okay, if it is a flat face, then you will call it a plane face follower. If it is a spherical face, somewhat spherical at the point of contact with the cam, then you will refer to it as a spherical face follower. Okay, I hope that was clear. Now, let us look at the dwell, rise, dwell cam, okay, the DRD cam. Okay, if we look at the motion of the follower, okay, it will be described by something like this, okay, and of course on the x-axis you will have the cam rotation. Okay, so on the x-axis here, what we have is the angular rotation of the cam. Okay, so it's going to be in degrees from 0 to 360. Okay, that's what you will have on the x-axis. And on the y-axis, what we have is the follower displacement. So for instance, let's say maybe when the cam is at 90 degrees, maybe we assume 90 degrees is here, then the follower displacement will be maybe that height there where it will meet. But the graph that is described by a dwell, rise, dwell cam is actually this graph, okay? And as you can see, the first segment here, it's dwelling, okay? It's more or less horizontal initially. So the first segment here, for a certain rotation of the cam, okay, it is dwelling. and then here it begins to rise. Okay, so from this angle of rotation of the cam to that angle of rotation of the cam, from here to here, okay, it rises. And then once it reaches this rotation of the cam from a certain angle here to an angle there, it is dwelling, okay, and then it falls here, and then it dwells again there, okay, it starts dwelling there. Okay, so this is pretty much the graph, the displacement graph of the follower, where of a dwell, rise, dwell, cam. Okay, we can also look at the dwell, rise, fall, dwell. Okay, and this is what it will look like. And as you can see, the first segment here, it is dwelling, and then it rises. Okay, so from a certain angle of the cam here to another rotation angle there, as it is rotating from that angle to that angle, maybe as it rotates from 70 to 210 to maybe 190, okay, then during that rotation it is rising, okay, and then after that it falls, and then it dwells again, okay. So this is pretty much what the graph, this is the graph of a dwell, rise, fall, dwell, cam will look like. Okay, the graph that describes the displacement of the follower, this is what it will look like when you're dealing with a dwell, rise, fall, dwell, cam. Okay, very important. And then you also have the rise, fall, rise, or rise, return, rise. Okay, triple R cams. And this is what you will have. As you can see, it rises and immediately it falls, and then it will rise again and fall. Okay, so it's rise, fall, rise. Okay, or if you want, rise, return, rise. Okay, so that again describes the displacement of the follower for a triple R cam. Very important. And so now let us look at situations where you have a follower that is moving with uniform velocity. Okay, when you have a follower that is moving with uniform velocity throughout, okay, the displacement of the follower can be described by this graph that you see here. Okay, so this will be its displacement as it is rising, and when it has risen completely, then the displacement for it as it is falling will be that curve. Okay, and of course on the x-axis you have the cam rotation. Okay, so when the cam is at 0, it's here. When it has rotated 15 degrees, it's here, 180, and then 360. Okay, and so this height that you see here, okay, this is what we will refer to as the rise or the fall, okay, of the follower. That is described by this height. So if you look at it on that axis, the value that you will read there will correspond to the total rise or total fall of the follower. And so this is what the follower displacement graph will look like when you're dealing with a follower that is having a uniform velocity, meaning it rises with the same velocity and then that falls with the same velocity, and so on and so forth. And so we can also calculate the angular velocity of the cam, and this is given by this, the cam's angular velocity, the cam's angular velocity is given by that, okay? And so omega is equal to theta divided by tan, but generally this is the equation that you will use because in most of the questions they will give you the angular the RPM. They will give you the RPM or the natural frequency of rotation of the cam. Okay, so when they give you n, okay, then you can get the angular velocity using that equation. Omega here is the angular velocity of the cam, and it's given in radians per second. Now, you can also have a follower that is describing a simple harmonic motion. And when that is the case, this is what the displacement graph of the follower is going to look like. Okay, so you still have the cam's rotation on the x-axis, and here you have the displacement of the follower until it has reached its highest value before it starts falling, okay? And sometimes you have a follower that describes a simple harmonic motion, okay? When you have a simple harmonic motion for the follower, then some equations are also in play, okay? So the first one, of course, is that of the cam. The equation for the angular velocity of the cam is the same, okay? In questions that you will get in your exams, they will generally give you the natural frequency of the cam, okay? Its frequency of rotation in RPM, okay? They will generally give you that, and you can use that to actually get the angular velocity of the cam. Okay, so that is the equation that you will always use to get the angular velocity of the cam. And you must not mistake velocities for the cam with the velocity for the follower, okay? It's different things, okay? So omega is the angular velocity of the cam, and you get it using this equation. Now, to get the velocity, the maximum velocity of the follower, you will use this equation, and this will give you an expression in meters per second because the follower is moving in a straight line, okay? It's not an angular velocity, and so this will give you an expression in meters per second. That's the maximum velocity of the follower, okay? Here is the angular velocity of the cam, which is actually a constant velocity. Good. And then you also have the maximum acceleration of the follower, which is given by this equation here. Okay, that is very important. At this point, I may already say that the follower will reach its maximum velocity at the middle of the stroke, okay, at mid-stroke. That is where the follower reaches maximum velocity. And its acceleration is maximum at the beginning of the stroke, and the deceleration is maximum at the end of the stroke, okay? So I repeat, the maximum velocity of the follower is reached at mid-stroke, okay? At mid-stroke, which means at the midpoint of the stroke. That is where you reach the maximum velocity of the follower. However, the maximum acceleration of the follower is at the beginning of the stroke, and then the maximum deceleration is at the end of the stroke, okay? I hope I made myself clear there. And so you can also have a follower that is moving with a uniform acceleration, okay? When I said maximum acceleration of the follower, this is when we deal with simple harmonic motion. I need to make that clear because somebody may say to me, you just said that the maximum acceleration of the follower is at the beginning of the stroke, but now you're saying you can have a follower that moves with uniform acceleration. No, you have to understand the context, okay? So here we're dealing with a follower that is following a simple harmonic motion. When you have that, okay, then in that case, the maximum acceleration of the follower is at the beginning of the stroke, and at the end of the stroke, that's where you have the maximum deceleration, okay? And so when you have a simple harmonic motion, the acceleration of the follower is not constant, okay? I hope that is clear. But you do have another case, which is not a simple harmonic motion, where you have the acceleration of the follower uniform, okay? So uniform acceleration, uniform deceleration, okay? So when you have that case, then for that case, the acceleration is constant throughout. And if we look at the displacement graph, this is what it will look like. And again, here, the angular velocity of the cam is given by this equation, which is the same everywhere, okay? And we can get the mean velocity of the follower when we have uniform acceleration, and that is the equation for it. And then the maximum velocity is twice the mean velocity, which is given by that. And then the value of the acceleration is given by this. And this acceleration is constant, okay? In this case, the acceleration is constant. But when you're dealing with simple harmonic motion, the acceleration is not constant throughout, okay? It is maximum at the beginning of the stroke, and it slows down eventually until it reaches its maximum deceleration at the end of the stroke. Okay, so you need to understand in which situation you are. Usually when you're reading a question, you will know whether you're dealing with a case of simple harmonic motion or a case of uniform acceleration or uniform deceleration. Okay, so if you're dealing with this, these are the equations you will need to use. If you're dealing with that situation, these are the equations that you will need to use. Okay, very important. Now let us look at some examples. The first one is a cam imparts a 36 millimeter stroke to a follower with uniform acceleration and deceleration during both the inward and outward strokes. Each stroke occurs over 50 degrees, okay, with a 10-degree dwell period at maximum lift, okay? So for 50 degrees, it rises, 10 degrees, it will dwell, and then 50 degrees, it falls, and 10 degrees, it dwells, just like that. Okay, so the cam will rotate through 50 degrees as it is rising, and then the cam will continue rotating for another 10 degrees, but then it will be dwelling, the follower will be dwelling, and then after that, the cam continues to rotate, and then now for the next 50 degrees, the follower will be falling, okay? So this is the situation that you have. Now, they want you to calculate the follower's maximum velocity and acceleration when the cam is rotating at 150 revolutions per minute. Okay, so you can pause the video here, just read the question again and see if you can make sense of a few things. Moving right along. So first we know that we are given the lift, okay? So S here is the lift. S is the lift, okay? Maybe I should have said that earlier, but I'm sure even at the bottom of the previous screen, you should have seen that S was the lift, okay? But if it was not there, I introduce it to you now. In all the equations that I pointed out earlier, okay? Everywhere you saw S, S was the lift, okay? And theta is the angular displacement, which must be in radians, okay? But this S is the lift. So now, since you are told that the stroke is 36 millimeters, remember I told you the rise or the fall, or if you want, you can say the lift or the fall is actually the stroke length, okay? So the stroke length, therefore, in this case is 36 millimeters. And so you turn that to meters, and this is what you will get for the stroke length, okay, or the rise or the fall of the follower, okay? And you are told also that you have a uniform acceleration and deceleration. That is a very important piece of information because it tells you which kinds of equations you will have to use. Okay, since you're dealing with a case of uniform acceleration and deceleration, we know for certain that this problem will not involve equations from simple harmonic motion, okay? So it's the other one. And so we are also told that the strokes occur over 50 degrees, okay? So when it is rising and falling, it does that over 50 degrees. So theta is 50, but remember, you need to change that 50 degrees to radians because theta is the angular displacement of the cam in radians, okay? So this is what we will do. We will change 50 to radians, and you will find that it is, you just need to multiply by pi over 180, and you will find it to be 5 pi over 18, okay? If you want, you can punch this in a calculator and find the number, but I do not like to do that because sometimes when you plug in the values in the other equations where you will plug in theta, you will find that pi will cancel out. Okay, so I'm just gonna leave it like this and we will carry on working like that. Okay, so we have theta like this. Another thing that we are given in the equation, in the question, sorry, is the number of revolutions of the cam. Okay, the cam is rotating as 150 rpm, so that allows us to get the angular velocity of the cam. The angular velocity of the cam is given by this equation, and so if you plug in with 150 there, okay, then you will get 5 pi radians per second for the angular velocity of the cam. And again, you will notice I did not work this out in a calculator. I just left it like that because, as I said earlier, as we plug in these values into the equations for maximum velocity and for acceleration, sometimes pi will cancel out. Okay, so it's better to just not work this out yet here. That helps you to have a more accurate answer, because if you tried to multiply these already, then you're gonna have to round off the number that you get and you will lose in accuracy as you move along. But since we have a lot of pi's in many of these values, we may just leave them like that, and then we will just simplify everything nicely at the end, and you will find that sometimes the pi's will cancel out. Okay, so now that we have the angular velocity of the cam, we can calculate the maximum velocity, okay, when we're dealing with uniform acceleration and deceleration. And so this is the equation for maximum velocity, and so we can plug in the numbers like that, and you will see that omega, which is the angular velocity, is 5 pi, and you will see that theta, which is the angular displacement during the rise or the fall, okay, is 5 pi over 18. Now, as you can see, you have pi in the numerator and you also have pi in the denominator, so that will cancel out. And so you can just punch quickly your numbers in a calculator and you can overlook the pi's because they cancel out, okay? And so what you will get for the maximum velocity will be 1.296 meters per second, okay? That is the maximum velocity. Since we're dealing with a case of uniform acceleration, we know the equation for acceleration. And again, we can plug in all those numbers like that, and you will find that your acceleration is actually 46.656 meters per second squared. And so if you can do that, that's pretty much all that was expected from you in this question, okay? You had to find the maximum velocity and also the acceleration, okay? Very important. This is not the maximum acceleration. This is the acceleration throughout, because you are dealing with a case of uniform acceleration. So the acceleration doesn't change. Okay, so this is what it is. Let's look at another more challenging example. A cam gives the following motion to its follower: 40 millimeter lift with SHM. Okay, somebody may wonder what is SHM. This is simple harmonic motion. Okay, that is what it stands for. Okay, so once you see that, you know that you will have to use the equations for simple harmonic motion. Okay, so a cam gives the following motion to its follower: 40 millimeter lift with simple harmonic motion for during 120 degrees of cam rotation. So as the cam is rotating through 120 degrees, the follower is rising by 40 millimeters. And then when you reach maximum stroke, okay, the follower rests, or it dwells for the next 90 degrees of rotation of the cam, okay, of the cam, sorry. Very important. So I hope you can picture this in your mind. As the cam is rotating through 120 degrees, the follower is rising 40 millimeters, and then when it reaches the top, the cam of course continues to rotate. Now for the next 90 degrees that it is rotating, the follower stays at the top because it is resting for the next 90 degrees. And then it returns now to the lowest position for the following 150 degrees. Okay, so after the 90 degrees, as the cam continues to rotate for another 150 degrees, the follower then folds slowly back to its original position. Okay, so for the first 120 degrees rotation of the cam, the follower rises by 40 millimeters, and then for the following 90 degrees, it remains there on top because it is dwelling, and after the 90 degrees, it begins to fall down, but it will fall through a rotation of 150 degrees of the cam. Okay, so I hope this is making sense. And so after that, they also gave you the RPM of the cam. Okay, the camshaft, it's 180 rotations per minute. And now they want you to calculate the maximum values of velocity and acceleration during the lift and return stroke of the follower. And then after that, you have to sketch the displacement, velocity, and acceleration curves for the follower, each with a cam angle of 360 degrees as a base. Okay, now this is more like an exam type question. I will show you how to do that, and you will find that it is not as difficult as it may seem right now. If you need to pause the video just to look at the question carefully again, you are welcome to do that, but we will move right along. So let's begin with question 1. Question 1, we have to calculate the maximum value of velocity and acceleration during the lift and return stroke of the follower. So we will have two maximum values for velocity and two maximum values for accelerations. Okay, one for the rise of the follower, and then the other for the fall of the follower. Okay, so first let us look at what is given to us. We are given the maximum lift distance, 40 millimeters, so that is S, as I explained earlier. Okay, and you are also told that the rise, okay, to that height takes place through a cam's rotation of 120 degrees. Okay, and so what is 120 degrees? It's actually the angular displacement of the cam, okay, during the lifting of the follower. Okay, and so this is, we may call it theta lift if you want, or theta rise. And we will need to change that to radians because we need to have our angular displacement in radians. So theta lift, which is the angular displacement of the cam during the lifting of the follower, is going to be equal to 120 multiplied by pi over 180 because we want to have it in radians. And again, even here, I did not simplify. I just left it like that in the hope that the pi will cancel out maybe later on in my equations. And so theta lift is given by this. And we can also get theta fall, okay? And theta fall, we know from the question here that when the follower begins to come back down from its highest position, the cam rotates through an angle of 150 degrees. So the angular displacement through which the cam rotates in order for the follower to come back to its original position, okay, coming from the top, that angle is 150 degrees. And so you need to also have the angular displacement for the fall of the follower changed to radians. Okay, so this is what we did here. Now, we can also get the angular velocity of the cam, and this is the equation for it. We know what is n, and n is 180 rotations per minute. And so we can plug in that into that equation, and that will give us the angular velocity of the cam. It's 6 pi radians per second. And again, as I said, I don't like to work this out at this point yet. I would rather plug it into those equations and see if maybe the pi's are going to simplify. But you are welcome. If you want, you can just work this out in a calculator already here. But I feel like it's a bit of a waste of time, especially if it's going to simplify later. Okay, so this here is the angular velocity of the cam, okay? Very important. And so now that we have that, we can then get the maximum velocity when you're dealing with simple harmonic motion, okay? You know what is the equation for maximum velocity and maximum acceleration. But what I want you to be able to appreciate here is that because we have different values for theta, okay, one for when the follower is rising and one for when the follower is falling, we're gonna also have two different sets of maximum velocities and accelerations. You will have the ones for when we are rising or lifting the follower, okay? And this is the equation for maximum velocity, but since here it's when we are rising, okay, then theta that we will use in the equation for maximum velocity will be theta for rise or lift, okay? And this is what you will have here. And then you can just quickly plug in the numbers, and after that, you find, of course, what the velocity is here, and you can repeat a similar approach when calculating the acceleration. This is the equation for acceleration, okay? But theta again will be that for rise or lift, and you plug in again the numbers, and this is what you will get. And so the maximum velocity for lifting the follower is 0.565 meters per second, and the maximum acceleration, you will find it to be 15.989 meters per second. Okay, we just plugged in the numbers in these equations. These are the simple harmonic motion equations for maximum velocity and maximum acceleration. We just needed to be careful in using theta, okay? Because in this particular question, theta is not the same for rising and falling, okay? The cam rotates through 120 degrees when raising the follower. But then to drop the follower, it rotates through 150 degrees. So theta rise and theta fall are not the same. So you need to know which theta to use where. So for lift, you use theta rise or theta lift, okay? And then for fall, of course, we will use theta fall, okay? So Vmax, same equation, but we use theta fall. And then you plug in the numbers. Theta fall is 5 pi by 6. Here we used theta rise, but here it's theta fall. And so 5 pi by 6, you plug in the numbers like that, you get that the maximum velocity that you attain during fall is 0.452 meters per second. And remember, this velocity is that of the follower, okay? It's not the velocity of the cam, okay? And as well as the acceleration that we find is that of the follower. So these are maximum velocities for the follower during rise and fall, and maximum acceleration for the follower during rise and fall. So the maximum acceleration during fall, this is the equation that we will use. And again, we use theta fall, okay? And plugging in the numbers, this is what you will get. If you do everything correctly, you will find that the maximum acceleration during fall that the follower can attain is 10.233 meters per second squared, okay? And that's it for question one. We found the maximum velocities and maximum accelerations, okay, during the lift and the return stroke. Okay, whether they say lift or rise, it's the same thing. Whether they say return or fall, it's the same thing, okay? Very important. And so now for question two, what they want you to do is to sketch the displacement, velocity, and acceleration curves for the follower, okay? You have to sketch it, and they tell you at the base you need to have the cam rotation. Now the cam rotation is from 0 to 360 degrees, okay, because you've seen how the cam is rotating, okay, it goes in circles, so it's from 0 to 360 degrees. So that is what you will have on the x-axis. Okay, so we're doing question number two. So we need first of all to remember the maximum values that we calculated earlier. Okay, we have the maximum velocity for lift and the maximum velocity for fall. we have the maximum acceleration for lift, and we have the maximum acceleration during fall, okay? And besides that, I will remind you of a few things that I stated quickly earlier, and and this will help you to actually draw these curves, okay? The first note that we're going to make is that the displacement, we will take the displacement to be 0 at the middle of the stroke, okay? So this is where we will take the displacement of our follower to be 0. We won't take the displacement of the follower to be 0 at the bottom of the stroke, okay, or at the beginning of the stroke, okay? We will take it to be at the middle of the stroke. That is where we will take our displacement to be 0, okay? Very important. And also, another thing that you need to understand is that before a stroke, the velocity of the follower is 0, okay? Because the follower hasn't started to move yet, okay? So velocity is 0 at the start of a stroke and also at the end, because at the end of the stroke, the follower is about to start moving in the other direction, okay? And so it may dwell there for some time, but the next time it moves, it will be in the other direction. So the velocity of the follower is 0 at the beginning and at the end of a stroke. However, as I said earlier, the velocity of the follower will be maximum in the middle of the stroke, okay? This is when all that I'm saying here applies to simple harmonic motion, okay? And so the velocity will reach its maximum at the mid-stroke. And what about accelerations? Well, as I said to you earlier, the acceleration is maximum at the start of the stroke, and it is 0 at the mid-stroke, okay? So you will have a maximum acceleration at the start of the stroke and a maximum deceleration at the end of a stroke, okay? And the acceleration or the deceleration is 0 at the mid-stroke, okay? So these are important things that you need to know for you to actually be able to draw the curves, okay? So now we will get into drawing the curves, okay? So the way to do it, I'm gonna take you through a step-by-step process on how to draw these curves, and it is not difficult, okay? So the first thing that you need to do is to draw a line for 0 degrees, okay? That is the first step. When you're dealing with a question of a cam where the follower is following a simple harmonic motion and you have to draw curves, the first step is to draw that 0 degrees line, because initially at the beginning, the cam is at 0 degrees. Now, in this particular question, you are told that the first thing that it will do is to lift the follower through 40 millimeters, and while it is doing that, the cam will rotate through 120 degrees. So the second line of importance is the line for 120 degrees. So you can draw that line somewhere, okay? So that is the line for 120 degrees, okay? And so the next thing that happens after the cam has rotated through 120 degrees is that it will rotate for another 90 degrees, but while it is going through that rotation of 90 degrees, the follower is just dwelling on top, okay? It's not moving, it's just dwelling at the position where it was taken before. Okay, so for the next 90 degrees, then the follower is up there at 40 millimeters. Okay, and so for the next 90 degrees. Okay, so that's what I meant to say. And so then what does that mean? If we are at 120, if you add another 90 degrees, the next line that you will draw should be that of 210. Okay. And if this is 120, this distance, so you try just and use your appreciation to try and draw a line for an extra 90 degrees, which will take us to 210, okay? So the distance between this line and that line is 90 degrees, okay? This here is 120 and that there is 90 degrees. And so if we are at 120, you add 90, you are at 210. Okay, so what happens during the first 120 degrees rotation of the cam? the follower is being lifted to 40 millimeters. When it reaches 40 millimeters, for the next 90 degrees, it dwells there at 40 millimeters. And then you are told then finally that the follower then is slowly dropped to its initial position as the cam rotates for the next 150 degrees. So if you are at 210, okay, you add 150, that gives you the line for 360 degrees. And again, 150 is bigger than 120, so the spacing I have between 0 and 120 must be bigger than the spacing I have must be smaller, sorry, than the spacing I have between 210 and 360, because here that distance is 150 degrees. Okay, so you need to use your common sense to draw your lines in a way that makes sense. Okay, so these are the 4 lines that you will begin your drawing with. And now you need to draw a horizontal axis for the displacement, for velocity, and also for acceleration. And so the displacement one is usually the one on top, okay? So this horizontal axis here is that where we see the cam rotation for the displacement, okay? And below the displacement, we will draw another horizontal axis where we observe the cam rotation for the velocity. And then we will draw another horizontal axis where we will observe the cam rotation for the acceleration, okay? So this here is 0, this will be 120, this 210, this 360, and the same everywhere on top here. Okay, so now that we have this, it is always important to also draw lines that will represent the place where the follower is at mid-stroke, okay? So, and where will those lines be? If the cam needs to rotate from 0 to 120, okay, while lifting the follower, okay, that will mean that the follower will be at mid-stroke when, of course, the cam is somewhere around 60 degrees, okay? So it is just safe to draw that line there, okay, which represents the mid-stroke during lift. And then we will also draw a line to represent the mid-stroke during fall. Between 120 and 210, for those 90 degrees, we know that the follower is dwelling, it is not falling. So it is falling between 210 and 360 for that 150 degrees, okay? That is between 210 and 360, it is falling here. And so if we draw a line for the mid-stroke while it is falling, that line will be somewhere there, okay? You do not need to calculate the values for it. You can just draw it because this will help you in making the curves, okay? So now, the first thing that I said to you was that the displacement is 0 at mid-stroke. So here, this is pretty much, you can look at it as the 0 line, okay? This line here is also the 0 line. And so displacement must be 0 at mid-stroke. Mid-stroke is here, okay? These are the lines for the mid-stroke while rising, mid-stroke while falling. Okay, so at the mid-stroke, the displacement is 0. So our curve for displacement must pass through this point because at the mid-stroke, displacement is 0. This is the 0 line, so it should be here. And since we're dealing with a simple harmonic motion, you always gonna start by drawing this curve like that. This is what a simple harmonic curve looks like. And of course, in your paper, you will just do it freehand, okay? You just do it freehand, but you must draw it like that because that is the shape of a simple harmonic motion, okay? The curve for it looks like this. And because we said that we are 0 at mid-stroke, and since the stroke is 40, therefore, here at the bottom should be minus 20, and on top here should be plus 20. okay? Because if this is the 0 line, below here you want it to be minus 20, and there you must be at plus 20, so that the difference from the bottom to top is, the distance, sorry, from the bottom to top will be 40 millimeters, okay? So these are numbers in millimeters, okay? And so this is how you will draw it, okay? And so now once you've drawn it like this, somebody may ask me, how did you know you must draw the curve like this? When you're dealing with simple harmonic motion, it is always like that, okay? So you will just freehand draw something of that shape, okay? And here you will write minus 20 in this case because it's 40, and on top there will be plus 20 because in the mid stroke it must be at 0. Displacement is 0 at mid stroke. Now, once it reaches that height, it goes through a dwelling phase for the next 90 degrees. So it remains here for the next 90 degrees, okay? So that is not difficult to understand. But after those 90 degrees, when the cam is now at 210, okay, it will begin to fall until 360. And again, here you need to draw a shape like that. This is the shape for simple harmonic motion, okay? You will draw a shape like that, and again it will go from plus 20 to back to minus 20 where it was, okay? So that is the displacement curve, and it is as simple as that, okay? Now we will do the velocity curve. Now for velocity, remember what I told you, okay, that the velocity is 0 at the start and the end of a stroke, okay? So this is the rising, okay, the rising phase, okay? So it will be 0 here and 0 there. That we know about velocity. But the next thing that we know about it is that it is maximum at mid-stroke. So the line for mid-stroke is here. So the maximum value for velocity that we will have will be somewhere on this line, but it must be 0 at the start and end of the stroke. And so the way you will do that here is that you will draw it like that, so that you have the maximum value here at mid-stroke and it is 0 here and there, okay? And so what will be the maximum value for the velocity during lift? Because this is the lift phase, you will take this value here. And so that is what you will write there, like that, okay? And then here it's the dwell phase. So when the follower is dwelling, it is not moving. So the velocity during the dwell phase is 0. So you will just draw a straight line here on the 0 line. And then once you are here, now it's the falling. And the falling will be here, but the maximum value of the falling will also occur at mid-stroke. So the maximum value for the falling curve for velocity will be on this line. And so we have to draw it like that, okay? And what is the maximum value of velocity during fall is this, okay? So you will draw it, you will write it here, okay? But remember, velocity is 0 at the beginning and at the end of the stroke. And so you will draw that you will write that number there, okay? So very important. And then once you do that, that's it. That's the velocity curve for a simple harmonic motion. And now we will look at the acceleration, okay? Now for the acceleration, remember what we said about the acceleration. The acceleration is maximum at the start of a stroke. So we will have a maximum value at the start. The start is here, okay? The lifting stroke is from here to here. So the acceleration is maximum at the start of the stroke. So it will be maximum here, somewhere here. And the deceleration is maximum at the end of the stroke. The end of the stroke is here. So deceleration, so its maximum should be somewhere there at the bottom, okay? And we know that the acceleration and deceleration is 0 at mid-stroke. So this curve the mid-stroke line is here, so this curve must pass here, because at mid-stroke you must be on the 0 line for acceleration, because acceleration is 0 at mid-stroke, maximum at the beginning and maximum deceleration at the end of the stroke, but in the middle 0. Okay, so if you draw it, it's something like that. Okay, and we know what is the maximum acceleration during lift. This is the number that we found. Okay, so this is the lift phase here. So that is the number that you will write here. On this side, it is a maximum acceleration, but here it is a maximum deceleration. Okay, it is maximum at the beginning of the stroke, the acceleration, and the deceleration is maximum at the end of the stroke. Okay, so this is what you will have. And then after this, you have the dwell phase. When the follower is dwelling, it is not moving, so its velocity is 0, and also its acceleration is 0, because it's dwelling, it's not moving. Okay, after the dwell phase, then you have the follower falling. Again, because it is falling, okay, you will have a maximum at the beginning and a maximum at the end, but at mid-stroke it must be 0. Now, because we were here, okay, so we will start from here and we will go like this, but we will pass through 0 and go back there. In this phase here where it is falling, you have to understand that the direction of motion of the follower is opposite to that during the lifting phase. Okay, very important. And so that is why we start here. Okay, and so we will start with what value? The maximum acceleration during fall is 10.233. So you can just start exactly here. Okay, you need to go a little bit up because it's 10, it's not 15, so it's a smaller value, so it's somewhere here that you will start, and you will make sure that you pass through the 0 because acceleration is 0 at mid-stroke, and then you go back there like that. And so that's what we will do, something like that. And here again you will write the maximum values of the acceleration. Okay, and this is what you will have. And if you can do that, then that's all that was expected from you. Okay, these are curves for displacement, velocity, and acceleration for a follower that is following a simple harmonic motion. Okay, with a cam that is rotating at 180 degrees and that follows these particular conditions. That is rotating at 180 rotations per minute, I meant to say, and that is following these conditions. Okay, so that's what I wanted to say. All right, so if you can do this, then you will be very comfortable solving any question on chems. I hope this video was helpful to you. And this is me. If you need to get in touch with me, you can use the number in the description. I have all the videos on all the modules for mechanical drawing and design N6. And if you want to get access to those videos, feel free to contact me again using the number in the description. Thank you.